Good morning, good afternoon, good evening, everyone. I appreciate everybody for connecting with us in this virtual conference. Hope you all doing safe and well. I'm Amartya, your host for this session, and today we have Mr. Sanjay, who is a strategist, corporate developer, entrepreneur, and an investor, and who has been in the oil and gas industry for over 25 years. So he's a co-founder of Evolve Collective, a consulting firm that specializes in strategic and financial advisory for energy-related companies. So Evolve is currently helping many tech-focused ventures in the energy sector to hit the market and also has a number of companies in their portfolio that are working towards improving the ESG goals of larger corporations and making the real difference. So before starting the session, I would like to let you all know that you guys can shoot your questions in the Q&A window, and we'll be happy to take your questions at the end of the session. So without further delay, let's start the session. And now the floor is yours, Sanjay. Over to you.
Great. Thank you so much. Good afternoon to everybody. I will be talking about methane, which is near and dear to my heart. So, as far as my agenda today, I'm going to talk about what is methane and why it's so important, especially to our environment. I'll give an overview. I'll talk about the oil and gas production value chain and talk about where emissions are coming from, and then talk about how complex this issue is, and again, how important it is for us to solve it. And that gets into more of the area of Chainsis in terms of data management and AI. There's going to be so much data in measuring methane leaks and being able to diagnose and figure out why we're having these leaks. And this is where Chainsis and other data solutions are important. And I'll talk about what the future looks like. So what is methane? May seem like a basic question, but methane is a main component of natural gas, which is second to oil, it's second to the oil in terms of energy, providing energy to the world. So natural gas is a huge source of energy for power and many other things that we use day to day. And unfortunately, it accounts for about 1/5 of the greenhouse gases that goes up in the air. And one of the bad things about methane is that depending on the study, it can be as much as 80 times worse to the atmosphere than CO2. I guess one of the positives of methane is it doesn't stay around for forever, but it does stay in the atmosphere for 20 years. So we have methane that leaks from oil and gas operations, the pipeline infrastructure, it gets into the atmosphere, and it's really causing a bad effect on the atmosphere, probably more powerful than CO2, in fact. So this is something that we need to address. And you might be wondering, well, isn't natural gas going away? Are we moving to renewables? And this is a chart that shows that the answer is no. We're going to have natural gas for a very long time. So on the left side, this shows natural gas production globally, and this is measured in trillion cubic feet. I'm sorry, this is in the US, and you can see how the natural gas production's increased. In fact, it keeps going up each year. And if you look at the US Energy Administration's forecast, the reference case, it really continues to go up, even though the world is trying to shift to renewables. So natural gas production is strong, it's high, and it continues to grow higher. And there's some other scenarios here, but even if you look at a downside scenario, natural gas is there's still a significant amount of natural gas being produced. And therefore, if we don't do anything, there'll be a lot of natural gas that just, and the methane within the natural gas that leaks into the atmosphere. So this is a big problem. So a bit of a complicated chart, but I wanted to put this up because it shows in the oil and gas infrastructure that there's lots of areas of leaks. So on the left-hand side, we have where the gas comes from, which is an oil and gas well. In some cases, we have wells that produce both oil and gas, and we have wells that produce just gas. And this goes into separation process, goes into a whole infrastructure of pipelines. In the US, there's probably about 1 million miles of gas pipe, and then it gets processed into a gas plant. The processed gas moves through compressor stations and even larger pipelines, and eventually gets over to our homes, our offices, factories, etc. Throughout this whole entire infrastructure, there's potential for leaks, particularly on the front end of this process, because here we've got literally 1 million wells in the U.S. that are producing natural gas, and then we have, like I mentioned, miles and miles of pipe, and each one is a relatively small volume, and so nobody has really gone out and systematically measured the the leaks here. When you get to these much larger pipelines that are taking uh, large quantities of gas, those do have sensors. And if you have a very high pressure pipeline, so if you have a small leak, you'll notice it. In fact, there would be no small leaks on a large pipeline. So this part of the infrastructure on the right is pretty well under control. It's really where you have the sources of leaks that are not being measured at all, largely today on the left side. And where can the leaks happen? On the production side, on this left side, you have controllers, you have gathering compression station tanks that leak, pumps. On the gathering and processing, these are the miles and miles of pipe. You have, again, compressors, gas engines. These are all different sources of leaks. Not to mention that just the pipe itself, they tend to corrode over time, can generate cracks, and those can leak as well. So there's just literally millions of sources of potential leaks that's largely not being detected today. This is, I thought, a pretty interesting chart that shows via satellite where the leaks are occurring. And wherever you see this deeper red color towards this end of the scale is where by satellite we're detecting methane leakage. So you can tell in West Texas and New Mexico, where there's significant oil and gas operations, a pretty deep color red. We have in California and in the oil gas producing areas here a deep red. And if we key in a bit more closely on the West Texas, you could see the areas of production where there's lots of oil and gas wells and pipe. We see very deep reds, meaning that there's a lot of methane coming into the atmosphere from these areas. So where you see the highest percentage of leakage are into the traditional basins, oil and gas basins. In the Permian, I mentioned, there's also other areas up here in the north in the Bakken and North Dakota that also have high production and high leakage. And oil and gas production makes up 68% of all methane emissions. There are other sources of methane that come from agriculture and other industrial emissions, but 68%. I mean, that's a big percentage is coming from oil and gas production, and this just shows where it's coming from. These are 20% of the oil and gas volume of leaks are coming from oil production. With a lot of oil production comes with gas, and then 48% is coming from mainly gas producing wells. And then you have about 30% that's leaking in the pipeline infrastructure. And I threw in these two data points here on this chart. These were done in a particular field in British Columbia, but this was a aerial survey. So this was taken from an airplane looking down and taking an image of where the leaks are happening. And just in a small area, over a couple hundred wells, they found 80 leaks, and it was scattered across tanks, their flares, compressors, etc. And then they also put sensors on the ground, and they found another 379 leaks. And then again, it came from yet another set of equipment, separators and compressors. But these leaks here were entirely different leaks than the leaks found from the air. And I put this picture here because if you take 379 leaks that were found on the ground plus 80, that's close to 500, 450 to 500 leaks, and just a small set of production. And the leaks that were found in the air were different than the leaks found on the ground. So this just suggests it's very complicated to be able to detect and figure out where all these leaks are coming from. So it's a huge detection issue, but you could also imagine that this was a point in time where they detected these 450 leaks. This is continuously happening. So if you imagine a world where you have sensors and you're taking aerial images, there's going to be a ton of data coming from the field that needs to somehow make it from the field into the cloud, get processed and interpreted so that people, the operators, know where the leaks are, how big they are, and what the potential root cause might be. So this sets up a huge data issue that I think will play, that Changes and others can handle, will need to handle in the future. So why should operators do anything about this? I mean, after all, the oil and gas industry has been around for almost 100 years, and we're just now starting to worry about it. And why is this? What's the pressure that oil and gas operators are feeling? Well, there's really three sources of pressure here. One is there's new regulation in the US that's coming in place. The first is from the Inflation Reduction Act, which was passed earlier. I think it was actually late last year, about a year ago, that has pretty significant expectations and requirements for operators to measure methane across their wells and their equipment. And next year is a bit of a year where an operator can measure a sample of their equipment and extrapolate that leak data across all their operations. So they call that a calculated emissions. But starting in 2025, everything will have to be measured. There's no modeling or extrapolation of just a sample set of data. So the amount of information or amount of data coming in will be magnified by orders of magnitude. And that's just from the Inflation Reduction Act. And if operators don't comply, there are pretty stiff penalties that will be imposed. And then the Environmental Protection Agency also has a set of regulation that should be approved next year. That's also will have a similar effect that will cover a broader set of facilities and pipeline, but also requires that there be direct measurement of methane leaks and not calculated. So that's going to mean significant amount of detection and data that will be required. That's from regulation, but many operators have already stepped up and are actually making methane detection and eliminating the emissions a big priority. And that has to do with investor pressures. So there's been significant pressure from pension groups and other large investors to force oil and gas companies to be more environmentally conscious. And they basically will say that if you're not being proactive in eliminating greenhouse gases, including methane, we will basically get out of your stock. And just as an example, I spoke to a leader in investor relations at ExxonMobil a couple of months ago, and she stated that one of the biggest pressures she has is to convince their big investors that they are being proactive. And otherwise, they may lose some of their large investors. And we're talking about large pension funds. So the last thing any large publicly traded company wants is to lose some of their big investor base. That would be very problematic. So the investor pressures are definitely encouraging many operators to step up their effort on methane detection and mitigating the emissions. And then finally, environmental groups are very active. The Environmental Defense Fund, which is an environmental group, is able to get satellite imagery from time to time and be able to look over oil and gas operations and be able to see who's leaking gas. When you're looking by satellite, the leaks have to be pretty large to be able to be detected. But nonetheless, these environmental groups can get a satellite image over an area, find a leak, And this actually happened to Apache, which is an oil and gas company, earlier this year, where an environmental group found that they had a leak. One of their flares was leaking gas, and they basically turned that information over to the press. And so the next thing you know, it was all over the press that Apache had this leak, and it caused a lot of frustration within the company. So the last thing I think you'd want as an oil and gas company is you don't know where your leaks are, but somebody on the outside does, and that's quite the embarrassing situation. So there are three pressures that are really forcing operators to really think about methane detection. This is what the Environmental Defense Fund or the Environmental Defense Fund found on the satellite. They found this plume of gas and basically turned this over to Bloomberg, which is a news agency, and this caught Apache off guard. So it's quite, there are watchdogs out there looking for leaks like this. And so it's incumbent upon the operators to be proactive in finding the leaks before anybody else does. So there are many different methods to detecting methane leaks. I mentioned satellite is the first one that will find major leaks, generally over 250,000 cubic feet per day. Just as an aside, there's many different ways to measure a unit of gas. What's common in the US is we use cubic feet, and and commonly we'll use 1,000 cubic feet as a basic measure of gas measurement. And so 250,000 cubic feet per day is quite a leak. In fact, it would cause safety issues if it was to ignite. It would cause a fairly big safety issue. So satellite detection actually was started probably 10 or 15 years ago to make sure there weren't any sizable leaks that would cause an explosion. But now it's being used in addition to find large methane leaks. The nice thing about satellites is you constantly get an image. It's almost real time, and you'll know at any point in time, that you do have a sizable leak that needs to be taken care of immediately. So that's a satellite. There's the next one is aerial technology, which is basically putting lidar sensors, radar sensors onto the bottom of an airplane wing, and periodically, let's say every 3 months or every 6 months, operators will fly these airplanes and look for leaks that are smaller than what you can detect from a satellite. So airplane sensors will help you find leaks that are about 10 MCF a day, which are really medium-sized leaks. The problem with the good thing about aerial is you cover all of your facilities, because it's basically like a lawnmower going back and forth, and you cover all the extent of your wells and your facilities. The big issue is it's not real time. You fly it every 3 or every 6 months, but in between you'll have leaks that pop up after you do the survey, and then they're not detected until the next time. So if I do a survey and then tomorrow a new leak occurs, I won't know about it for 6 months. And so for the whole entire 6 months, I'm leaking this gas into the atmosphere. So it definitely has its disadvantage. And then the final is on the ground sensing, which includes drones, people that will take handheld sniffers, and then actually installed sensors that are permanently installed that will detect gas. There's a whole myriad of different types of sensors, ranging from optical cameras that actually will take an image and detect a methane cloud. That's very data intensive, very image intensive, and very costly. So you'll only see the optical cameras around major facilities, like major plants. You generally don't see them across the millions of wells that we have, or the smaller pipeline. So where the on the ground sensing is probably headed is very low cost sensors that you can install around all your major pieces of equipment around the wellhead, et cetera, that would then provide a real-time picture, a real-time sense of, when a leak happens, you'll know about it immediately. So there's a lot of development still happening on the on-the-ground sensing area, but I suspect this is going to grow in time. So digging in a little bit deeper about on the methane on the ground, I have a picture here of a very simple oil and gas operation. Here are here where the gas production is occurring with these pumping jacks that serve as a way to pump oil and gas out of the ground. And here's the various pieces of pipe and equipment around these wells. And then you finally have compressors and tanks. And wherever I have a blue dot is a potential source of a leak. You can have leaks at the well. You can have leaks at the various at each of the pieces of equipment. You can have leaks around the tanks, and actually you can have leaks in any one of these pipe that you see here. Now, if you imagine a world where we do put sensors on each of the blue dots, and we start to collect data, the data would tell you, in the simplest way, would tell you if there's a leak or not. So imagine you have a leak here on this well. This sensor will basically indicate, yes, there's methane in the air. But if there's a wind going across this facility or this operation, very quickly the wind will take the methane over to here, and all of a sudden this sensor will go off, and then over to here, and this sensor will go off, and then this sensor, and so forth, all within, let's say, 15 to 30 seconds, and maybe even faster. And so all of a sudden, all these sensors will start to indicate a methane leak, but you won't know where the leak is occurring. You won't know that it's specifically right here at this well. This poses a huge problem because then you still have to send somebody out there with a handheld piece of equipment, go around this entire facility to actually find that there is a leak. And oftentimes, these sensors are not accurately reporting. There may be a methane leak that happened a half hour ago, but it's no longer leaking. And then you send somebody to go find the leak, and he or she can't find it. It just wastes a lot of time and money. So ideally, what you like to do is have these sensors here pushing the data into the cloud, and then having the data interpreted in such a way that you would be able to know that the first sensor that started to record methane was this one, and be able to have the algorithms and be able to look at the data series and say, this was the one that went off first. And oh, by the way, we think because of the way the cloud spread to these other sensors, we think the leak is of this size. So now we can start to pinpoint through the data management and data interpretation where the leak is occurring and potentially how big it is, so that we can know where exactly to go look to fix the issue. So this is a huge big data issue, and it's pervasive. I've talked to operators that have put some sensors into their operation on a pilot basis, and there's some frustration about not knowing exactly where the leak is when the sensors start to indicate that there is a methane leak, and not being able to know the size. So this is a big issue, and I think this is where some Chainsis comes into the picture to be able to manage the big data, to be able to analyze, to be able to separate and look at the time series, and be able to pinpoint exactly where the leak is. That would be a very huge accomplishment. So because operators are going to use satellite, airplane data, and on the ground sensors, we need to be able to process large volumes of data from different detection sources. So if you go back to satellites and airplane surveys, there's a ton of data that's coming through, and it needs to be processed. It also needs to be processed against a geomap so that when you look at the piece of data, the methane data, you also know exactly where it is based on the geomap and being able to integrate those two together. So data management and the data flow is super critical to being able to solve this problem. We need to first be able to handle big data, to integrate various sources of data from the satellites, from and also be able to take in meteorological data like wind direction, other aspects. Humidity also causes an impact on how methane spreads. So being able to take the environmental data along with the methane data and being able to integrate that and interpret it is very big. Um, but we want to also get into a place where we're not just detecting methane and being able to say, yes, my leak is here. We want to be able to get into the area where we can predict why the leak happened in the first place. Is it something operationally that people are doing incorrectly? Maybe they're letting pressure build up, or they're not doing proper maintenance on the compressors, or it could be compressor seals are wearing down too quickly, and the operator doesn't know that, or it could just be an inherent design flaw in the equipment itself that's causing the leak. It could be corrosion issues. So right now we're in the world of just trying to understand where there's a leak, how big it is, and how important is it for us to fix that? Where does it sit on the priority list? But we want to be able to go back and say, the reason we have the leak in the first place is because this piece of equipment or the way we operate or something else. So this is where predictive analytics becomes really important. Being able to take all this methane data and integrate it in with the type of equipment and the way the operations is being run to be able then to predict and even mitigate future leaks. Because otherwise you'll just constantly have leaks pop up, detect and fix, and that's just an ugly cycle. So step one is detection. Step two is data processing and being able to understand the data and to be able to figure out how big the leaks are and where they are. But then the next step would be to be able to design predictive analytics around that. And then the final piece is because of all this regulation, we need to be able to provide the regulators with the information they need to know that the operators are complying with the rules. So that means that we want to be able to take all this methane data, interpret it, but also be able to produce reports that we could send to the federal government and say, yes, we are measuring everything that you asked us to measure, and we are complying. Where we find leaks, we are taking care of it. And oh, by the way, this is how much methane emissions we have avoided because of our entire process. So we could report that to the government. We could also report that to the investors and others and say, look, we've reduced the methane emissions by so much. That whole measurement, compliance, and being able to demonstrate a benchmark improvement is very critical. And that needs to come out from all this data as well. So just a large amount of data coming in, the need for predictive analytics, and the need to be able to let regulators know, investors know that we are measuring and making improvements are super critical and rely very largely on data management. So this is just a bit more, or a bit digging deeper into the why digital is critical in this area. I already mentioned data integration. We need to be able to integrate data from sensors, from airplane radars, from satellite imagery, then be able to pull the entire picture together for an operator, or an operator will need to have this done. And so I think this is where Chainsys can come in with the data cleansing, the data structuring, being able to put the analytics on top. The advanced analytic techniques is super critical, because once you want the operator to have confidence that when they see a leak, that the leak is real, they know how big it is, and they know where it is and what they need to do to go fix that. And that requires being able to process all the wind information, humidity, the atmospheric conditions, as well as being able to take all the data from the sensors and being able to make sense of that. So very critical on the data analytics. Predictive modeling, I talked about that on the earlier slide, but again, this is important to be able to forecast why, or be able to say why emissions are happening in the first place, and then be able to forecast where emissions may occur in the future, to maybe even perhaps say, you know what, if you don't fix this piece of equipment in about 2 months, it's going to corrode and you'll have a leak. So let's go fix this piece of equipment before we have a leak in the first place. And that way we get to zero emissions. We need to be able to integrate the geographic GIS, geographic information systems, because again, we need to know not that it's just this well with that's leaking, but we also need to know where this well is specifically. So being able to integrate the GIS coordinates in with the operations is critical. Regulatory compliance, we need to make sure that the collected data is being used to is sufficient to comply with methane regulations. We can establish automated reporting processes for the operator, for the government agencies, and to make sure that everything is meeting compliance rules. And then reporting communication, as I mentioned, being able to generate reports, benchmarks, et cetera, to be able to communicate the improvements to various stakeholders, including your regulatory agencies, the public, investors, is very, very critical. So you can see how the data management, the algorithms, being able to process the data and to put some AI on top is very critical to meet all these objectives. So we're probably this is a process where right now the industry is at the place where they're just now starting to detect methane using the different technologies. We are far from having a data solution that I talked about. But I think the nirvana over the next few years, we need to get to a place where we're doing the emissions monitoring, we're pulling the data, we have digital solutions, and then we're able to report and also control our operations to mitigate emissions in the future. All this integrated is really where we need to head. So what needs to happen generally is improvement in sensor costs. Those little blue dots I put onto that oil and gas operation, the costs need to come down. They are. Now you could probably find sensors that are a few $100s, which before they used to be several thousand. So the costs in sensors are coming down. We need to be able to integrate data, as I mentioned, from different methane detection sources, from satellite to the on-the-ground sensors. We need to be able to scrub, manage large amounts of data, put machine learning and AI on top. We need to, importantly, be able to control some of the equipment at the edge, meaning that if there is a big leak, we don't have time for the data to go to the cloud, process it, and then be able to then take action. We have to take action right away to be able to eliminate that methane leak. So some of the computing power needs to be in the field with the rest in the cloud. We need to be able to size the leak and have confidence in where the leak is happening. We need to be able to prioritize the leak. I mean, there's a certain, if you have 50 leaks and you only can get to 10 of them tomorrow, you want to be able to prioritize the 10 biggest leaks, obviously, to be able to take care of have the largest impact on emissions. Ability to take leak data and translate that to reporting, as I mentioned, and then we need benchmarking for investors and environmental groups. So it's a big plate, but I think Changes and others can help pull this together. Thank you.
Thank you so much, Sanjay, for this wonderful session. And now it's time for the Q&A, and we got a couple of questions from our audience.
Okay.
So the first is, when will regulation go into effect on methane reporting and mitigation? So if you could tell us, you should share some insights on this question.
Yeah. So next year there'll be, I would say, some reporting required That Inflation Reduction Act I mentioned will require that a few facilities get directly measured,
Mm.
and then the operator can extrapolate that to other facilities and turn in that information. Um, and if the facilities are leaking, they'll have to do something about it and show show the government that they did take care of it. But starting in 2025, there'll have to be measurement across most of the facilities. So there's no longer a modeling or extrapolation that would be satisfactory. You have to have direct measurement of the facilities, and then that covers a lot of the oil and gas production facilities. The EPA is also putting regulation that should be in place in next year that's requiring all facilities, including pipeline facilities, to have a baseline measurement. So in 2025, here's a baseline, and then they require a certain decrease off that baseline each year. So every year you have to turn in a reporting across all your facilities that says, yes, I have taken out the required amount of methane. And so that'll be I think a 5 year step down.
Okay. Okay. Interesting. Interesting. So the next question that we got from the audience is like, what are the operators doing now in terms of methane detection and mitigation?
So if I could go back to uh, this slide. So generally, operators are piloting all these different technologies. So they're in the pilot stage. So meaning they will take a part of their operations, a small part, and experiment with aerial, experiment with different sensor technologies, and try to pull the data themselves, or maybe they'll have a data provider interpret the data. But it's very much on the pilot stage. They're trying to figure out, and they may pilot 10 or 12 different technologies. They may be piloting, I should say, right now. With the goal is to figure out which two or three that they really want to go with and scale. So they're trying to figure that out. My prediction is that most operators would still use some satellite, because satellite is basically telling you, do you have something huge? They'll use aerial because aerial covers everything, meaning that if you have just a, a section of pipe and nothing else for about 10 miles, the aerial will cover that. And on the ground will be required to be able to detect the small leaks 24/7. I think on the ground is probably going to be the majority of the solution, but they'll still keep aerial and satellite. But this is still in the piloting stages where companies are using 10 to 15 different technologies. They'll get it down to three or four, and they'll scale that across their operations. And then, of course, the regulation timing will force them to scale.
Okay. Interesting. So now we got another question, like how does one get such a solution adopted? So if you could share something on this question.
How does one? I'm sorry. Say one more
How,
time.
how does one get such a solution adopted?
I'm guessing from a data solution adopted.
Yes, 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 yes.
Yeah, I think what needs to happen is uh, I think what needs to happen is really a marrying up of the detection technology with the data solution. They probably can't be right now. It's separate. Right now, an operator goes and hires a detection service, whether it's the airplane or sensors on the ground, and that data that the company they hire can handle that piece of data, but there's nobody integrating it all together
Mm.
um, in a whole scale. So I think there's opportunity for operators to realize that there's going to be data from multiple sources, and the amount of data is going to climb exponentially. That they should also bring in Chainsys as part of the methane solution. Now, you don't think of Chainsys and methane solutions. You don't think of methane detection. Chainsys is not the first thing you think of usually, but it probably should be one packaged up because Chainsys won't make the sensors, but they will be required to pull all that data and to be able to process and manage it. And I think that's a piece of the solution that I think probably we need to talk to operators, but then operators will also realize they need a Chainsys type solution So I think it's early days, but I think it'll come to where that digital piece needs to come in along with the core detection technologies.
So the last question, I think, is like how can changes play in this field? I think you have mostly covered with this question, but if you could add a few points, on this question, like how can changes play in this field? So I think that would be great.
Yeah, I think Chances should maybe talk about how the big data, the data cleansing, the data structuring, the data architecture can be applied to methane, maybe more of a direct communication to these operators, because I think that would probably um, I've seen a few operators say, yeah, let me talk to Chances because I've been looking for something like this, or I'll need something like this maybe 6 months or 12 months down the road to integrate in. So I think making a bigger maybe messaging and being able to explain how Chances capabilities can be applied to this area would go a long ways to the operators being aware that, yeah, let me talk to Chances as I'm developing, as the operators developing the holistic solution.
Cool, cool. So yeah, thanks. I think thanks and thank you, Sanjay, for this wonderful
Thank
session.
you.
And once again, thanks to everyone for joining this conference. Once again, like let's go to let's join the next session, which starts I think at 4 p.m. And once again, thank you everyone, and bye.
Thank you.